Greetings, students in artificial intelligence. And I know that you want to get started on neural networks. And I'm sorry to disappoint you. We will get started with a neural non-network. I call it a neural non-network because it has one neuron, but you have to understand the one neuron before we can get to actual networks. And later we will train a single neuron non-network. And that will be like the hello world of neural networks. So the main notion is that a neuron here is a metaphor, and the relationship between this metaphorical neuron and real neurons is kind of irrelevant. So we will think right now using this online tutorial. This is the URL, and there's a link posted in Blackboard. The task we're going to be looking at is a classifier task. So if you've had the basic data sciences or machine learning, you understand what a classifier task is. And it's picked because it's the type of task that frequently, uses us humans do. If you are looking at a picture and you need to decide whether it's a cat or a dog, or even an image from your eyes, and you're trying to decide what animal it is, that's a classification task. You're taking the input data, the image, and you are assigning that image to one of several categories that you know about: cats, dogs, other animals. Looking at images of a face, deciding which person it is. Listening to a song, deciding which song it is. There's a finite number of songs that you know about, and you hear the song and you put it into the category. That's a classification task. So we're going to look at how you might use a single neuron, non-network, to apply it to a classification task. And in this tutorial, they start with this picture over here. And the classification task is this a cat? So what? So we're not going to think about presenting the entire image. We're going to extract features from this image, and we will evaluate whether or not those features will help us to make the decision to categorize this as a cat or not. And this is pretty typical, even when you've got images that are coming into the neural network. The images tend to get processed to extract features out of the images in various ways. And if you've done any data mining, you're accustomed to this process. So if I asked you, is this a cat? You or I could point to the various things we see in this image. We see what? We see a unicorn horn. We see 4 legs. We seem to have some kind of paws on the bottom. We see a tail. That's good. We see whiskers. We see something that looks like a wing. All right, we see 2 eyes. So these are the various features, and some of them argue for it being a cat, and some of them argue against it being a cat. So what to do? How can the neural network deal with that? Well, the main idea is each of those features is going to go into the neural network. So we're going to have a single neuron, and the single neuron will try to combine information from here. It's 5 different inputs: the horns, the eyes, the legs, the wings, and the tail. So that's how this is going to work. And when you're training the neural network, normally you'd give it a whole bunch of images, and for each image you'll have these 5 characteristics of that image, and typically you'll have the correct answer. So you'll start with a bunch of different cases a bunch of different images like the one we just saw, and whether or not there's a horn there or something that looks like a horn, whether or not there's something that looks like wings, looks like a tail, like that. And for each image, you'll have the correct answer. So what do we need to do with those features? Well, the answer starts with most neural network inputs are not yes-no binary values. They can be, and that works, but a lot of times what you have is real numbers. And typically those are real numbers at roughly in the range of 0 to 1 or -1 to +1. Over here, this is saying that that thing which looks like a horn, sort of like a horn, we're like 83% match to a horn. We're 83% sure that it's a horn. The wings, okay, that's 72% like a wings. We're 95% confident that that's two eyes. Okay, we're only 50% confident that that's a tail, and if you look at it, you can see why. So, for each of these features, we have a numeric value from between 0 and 1 here. And those numeric values are going to go into this neuron. Now, the next thing you need to ask is, how important are these features? All right. The presence of a horn is pretty significantly saying that it wouldn't be a cat. Okay. The presence of two eyes, well, there's a lot of different animals that could have two eyes. So it's important, but okay. And here we have the four legs, and so we're going to assign what's called a weight value to each of the inputs. So the weight value comes with the network. The network is saying this neuron has these 5 weights, which says that the value of the horn feature is going to be multiplied by 0.87, whereas the two eyes feature is going to be multiplied by 4.2. So we can have a lot of confidence that there are two eyes, or we can have small confidence, and we can have a belief about how important it is. Notice that horns are against a cat decision. Eyes are for cat decision. So these weights can be positive and negative. The red weights here are negative. Horns and wings argue against it. Eyes and legs argue for it. So now we've got some numbers that can go into our decision. We have for each of those features how confident we are of that feature, and then for each of those features how significant it is. How do we combine all of that information to try and make a single decision? Well, the answer is this is going to just be a linear equation. And it's going to be feature 1 times weight 1 plus feature 2 times weight 2, the dot product of the feature vector times the weight vector. And not shown in this example is that there's usually also a constant term. So the main idea is going to be that these features are going to be multiplied, these feature values, by these weight values. And that'll give us a number. And what we could do at that point is we could just say, here's a threshold. Maybe we could say it's above 0, then it's probably a cat. Below 0, it's probably not a cat. Here we're getting minus 0.15. I would tend to agree. This is, kind of fishy for a cat. So that would be a linear classifier. But the next question is going to turn out to be, especially because we're going to be building neural networks with lots of neurons, what's actually going to happen is that the output of this linear equation, the result of this linear equation, the combined results of all the feature values and the weights we assign to each feature value, is going to go through something called an activation function. here it's a sigmoid function, but here's the input, and then along the x-axis, and the output is the y-axis. So why do we do that? So the short answer is so that we can have if statements. We could have neurons which, if the result becomes negative, then they just produce no output at all, but if it's positive, then they're considering the values. So, I mean, essentially it would be like an if statement which just shuts off. If the output of the linear equation is below zero, then that becomes zero, and it's not considered anymore. It doesn't become negative, it just becomes zero. It doesn't go into the rest of the network. So different neurons, and if we have an activation function which always produces zero on the negative values, then that neuron becomes like an if statement. If this combination of things is true, then consider its output. If that combination of things is false, then its output doesn't go into the final computation. So that's the kind of intuitive notion as to why we have an activation function. Generally speaking, if the neurons were always linear, we could just combine all the linear functions from the different neurons which are feeding each other, just feed each linear equation into the next linear equation, and we'd have one big linear equation. So we wouldn't be able to do anything more sophisticated than a linear equation. This sigmoid thing, you'll notice the characteristic is that small differences in the middle of the curve are significantly changing the output, whereas when we're up here in the x values, then small changes are only very slightly changing the output. So it has an effect kind of like not the binary effect of an if, it's true or false, but has the effect of, in some regions of this curve, changing the weights produces significant changes, and in other regions of the features, small changes makes less significant output. So it's kind of the same effect. Anyway, eventually the output of the inputs of the weights the inputs are multiplied by the weights. They're added up. They go through the activation function. We get an output. And the basic idea is then, if we wanted to make a classifier, we could then put in a threshold. Above the threshold is a cat. Below the threshold is not a cat. All right. I'm going to stop this now, and we'll do one more short video.